Welcome to all. We'll discuss in the previous class. We have discussed about point groups and we left with highly symmetric point groups. So today our discussions will be on highly point groups. Highly symmetric point group. Highly symmetric point group. So in these highly symmetric point groups, these are special types of point groups. These are special kind of point group. Why? Because these are in shape of regular polyhedrals. Regular polyhedra. So what this regular polyhedral means? They are in closed figure. In closed figure. They are in closed figure. What do you mean by that? In closed figure. So what do you mean by that closed figure? Let's say if I talk about if I talk about that let's say so these regular polyhedrons, let's say if they have the vertices. So if they have vertices, so let's say all vertices are equivalents. It means if you rotate along the vertices, then you get the equivalent orientations. It means if we do symmetry operations along the vertices, we get symmetry, we get equivalent orientations. Similarly, what now? They have all like edges are equivalent. Means if you do any operations along the edges, then also you get equivalent orientations. So similarly, get the equivalent orientations. Similarly, if they also have all vertices, edge, and another things is faces. All faces are equivalent. It means if we do the symmetry operations along the faces or edges, then we get the equivalent orientations. So these molecules are highly symmetric. So these are regular polyhedrons, polyhedral, and they have the closed figures. Closed figure since they are all vertices are equivalent. If you do the operations along the any vertices, you get the equivalent orientation. Similarly, if you do the operations along edges, then we get equivalent orientations in spaces. Okay, so if you have one, like past we'll discuss about the tetrahedron that is represented by TD, then this type of molecules, what says that tetrahedral means one triangle we will do. So let's say this is one triangle. So if this is the vertices, then what I say is that these triangles and this down one triangles, let's say this is above one triangles, and this down one triangles, let's say which color I will do, this down one triangles and and one triangle is these sides. Then one triangle each. Like that, and also another triangle is like that. Means all the four triangles are, so for this this pink and this green and this color, they have the common vertices this. Okay, so these all the tetrahedrals, but they have the common vertices, and they are, if you rotate, if you do any operations along edges or along faces, so here four spaces are there, that is 1 2 3 4, 1 2 3 4, so four faces. So here tetrahedron, all four faces are equivalent. Equivalent means that if you do any operations along this spaces, along one spaces, we get the equivalent orientations. And it has how many vertices? 1 2 3 4. So this is a 4 vertices. So for all four vertices are equivalents. Similarly, how many edges? 1 2 3 4 5 6. So all 6 edges are equivalents. Means if you do the operations along faces or vertices or edges, then we get the equivalent orientation. So I mean that huge number of symmetric operations are there, means symmetry elements are there. So the huge number of symmetry operations we will get for tetrahedral TD. Similarly, if you talk about of octahedrals, so TD, similarly if you talk about of that octahedral cases, like that, we have that here 6 faces, all 6 faces are equivalents. Like that, there have the vertices and edges, means these are actually the groups with having lot of symmetry operations. Similarly, for icosahedron, that is represented by IH, this is has approximately 12 faces. I mean 12 faces, or that is 20 faces. This is 8 faces. 8 faces are equivalents, and this is 20 spaces are equivalents. Means there have the huge number of symmetry operations are there. So if we talk about of that these groups of IH symmetry elements and OH symmetry elements and ED symmetry elements, then it is very, the symmetry operations are huge amount, so it is not possible to remember. So I have listed it. Let's say for cubic point groups, for tetrahedrals, the point groups are E, 8C3, 3C2, 6S4 and 6 sigma D. So total operations or that is called order of point groups, that is represented by H. Total H, we can count 6, 6, 12, 12, 3, 15, 15, 1, 16, 16, 8, 24. So 24 operations are there. 24 number of symmetry operations. Total symmetry operations, that is also called order of point group, or that is represented by H. 24 operations are there. Similarly, for octahedrals, here total symmetry operations, that is also called order of the point groups, that referenced by h. Total is, we can count, this is 6, 6, 3, 9, 9, 8, 17, 17, 6, 23, 21, 23, 1, 24, 24, 3, 27, that means 33, 33, 6, 39, 39, 40, total is 48 operations are there. Similarly, for icosahedrons, order of point groups H, that is equal to 120. So huge number of symmetry operations we can see. So this not needed to remember, but you have just idea that PD has highly symmetry groups, and these point groups are these, means this number 24 number of operations, this has 48 number of operations, this has 120 number of operations. So icosahedrons has second highest number of symmetry operations, followed by C infinity, B, and D infinity H, because here that infinity number of symmetry elements is there, because this is infinity, right? So infinity number of element is there. So this is the first highest number of symmetry operation, then comes that icosahedrons. Okay, so these are the about of that point groups. We have discussed all types of point groups, that point groups having no CN axis and having one CN axis and having that more than one CN axis, that we all discussed. So now another point groups is left, that is S2 and S and SN point group. So in this SN point groups, what the symmetry elements are there? E plus Cn plus ECN plus I. So this type of point groups elements will be there for the symmetry elements. If I draw the picture, then that picture will look something like so if I draw here, and if I draw here and Florence, then again I have to draw Florence, and that is it. The picture is something look like this. Okay, this will be okay. So now if I draw here, then I leave one. So now what I do, here F, then here F, then I will draw here F, then here F. So this the point groups here, and that in this point group no sigma plane is present. So no planar symmetry should present. Symmetry should present. Okay. So this point groups lies in this is the example of S2N point groups, and the elements are E. Sorry for the interruptions. So for this E, and that is Cn plus H2n. These are the symmetry elements and no Cn. Okay. And now, so we will list it out all the symmetry elements. So what I have to talk summary. If I give the summary, then we have discussed one that is containing one group. First category is group with no rotational axis, group with no rotational axis, no rotational axis, that are CS, Ci and C1. And second types we discussed with group with one rotational axis, that we discussed, that is Cn and Cnb and Cnh. And we have discussed that group with Cn perpendicular to Nc2 or more than one rotational axis, or in these groups, dihedral groups, that we have discussed Dn, Dnh and Dnd. And that special groups we have discussed, special groups, that is linear, that is C infinity V and D infinity H. And at the last what we discussed, that Sn axis, that is S2n, only one group, that is S2n. And last we have discussed, that is octahedral cubic point groups, that is more than one, means more than one or more than two Cn axis, means use one Cn axis and more than one Cn axis. Later you can say that we have what type of groups? TD, we have TD, IH and OH. So including this also the symmetry elements are there. Let's say this TD and IH and OH, if I remove from this sigma plane, then this will become T, because this is T, all the symmetry elements with sigma D. So if I remove everywhere from sigma, then here sigma H is removed, so it will become T, and this become I, and this become O. Like if I say TD groups, if I remove that sigma planes, that is become T. If I IH groups, if I remove sigma planes, then that will become T groups, I groups. And OH, here if I remove sigma, then that will become O. And these are obviously subset of these groups, means these are less symmetric compared to TD and IH and OH, because these are the after removing sigma plane we get this one. Okay. Another point groups we have, that is if we have T plus, if I add the sigma H planes, then we get TH. Okay, so these are all that. So if we listed out with this point group also presents, T, I is present, O is present, after that T is present. These are the more than one CNX point groups, means highly symmetric point groups. Highly symmetric point groups. So now we will discuss, after talking about all this, so we can make one table that, so we know that how these groups will come, right? So we will make one group, one table, that is, let's say a molecules is there. So how to say that this molecule lies in which groups? So first what we will do that here, now we will say that whether this is linear or not, whether linear or not. This the questions. They ask the questions, and if it says that yes, y means yes, no means this is no, n means no. Okay, so if it is yes, then another questions I will ask that whether it has sigma h. This one also we can ask, or we can ask whether it has I, or also we can ask whether it is Cn perpendicular to NC2. So any one questions, either you can ask this or this or this. Anyone if you asks, this is the questions. If this is yes, and if it is no, sorry, no. So if it is yes, then that point groups will lie on yes, means that we will D infinity H, and if it is no, then that is C infinity B. Okay, so this because we know that C infinity B, H no I, or no sigma H, or no Cn perpendicular to NC2. This things is not present in C infinity. With D infinity, this things is present. Now what I look, and now I'm going to look another things. Now what I will do that I will ask one questions, but whether, so this is no, after that no. Okay, whether more than one Cn axis. Here more than one Cn axis means Cn is there with that Cn minus 1 with that S, means this is actually whether more than, it is better to ask that whether more than 2 to more than 2 Cn axis, like that means questions. Then if this questions is asked, then if no or yeah, yes. So if no, then what is come, then now I will ask that if whether sigma h present or not. Okay. Whether sigma h is present or not. So if sigma h is yes, and this can also be no. So if yes, then that is C NH, and if no, then I will ask again whether sigma is present or not. So if sigma is present, yes, then that is C N B, and if it is no, then that is simply Cn. So we know this how to get this molecule. So I'm just applying that whether sigma is present, yes, then sigma NB, and if not, then Cn. And if sigma H is present, then that is CNH. Okay. So this can we can say that Cn, Cnb, this is one rotational axis. Now here also we can do one more things. Sorry. This is no. Okay. Now again we will ask that whether one rotational axis present or not. This is the questions. So if it says that is not more than 2 Cn axis, that is no. And if no, then whether one rotational axis is present or not. Whether Cn axis is present or not. Whether Cn axis present or not. This is the questions. Now if it says that no, then I will ask that whether sigma is present or not. Now I will ask that whether I is present or not. So if yes, then that is C, that is CS, and if no, then I will ask no, this is CI, and if no, then I will ask whether sigma is present or not. So if says that yes, then that is CS. If says no, then that is C1. This is CS, this is C1. Okay, so this one we can say. And now it says that whether CNX is present or not. So if CNX is yes, then if it is present, if yes, then now what will say that whether sigma h is present or not. Sigma h is present or not. So if sigma h is present, then if yes, then that is CNH. And if says that no, then what we will ask that again whether sigma is present or not. And if it says that yes, sigma is present, then that is C and D. And if says that no, then that is Cn. Okay, so this actually we declare that concept, then this is very easy to point out that. Okay, that we can draw by yourselves, that how to draw this group tables. Okay, so now whether more than 2 CNXs, if yes, so here whether CNX is present or not, this is yes. After that we can go to sigma h. After that, but we ask another questions here. What here we ask another questions that whether Cn perpendicular to NC2 is present or not. Present or not. Okay, so here if says that no, then we will ask these questions. And if says that yes, then again we will ask that same questions, whether sigma h is present or not. So if says yes, then we will go to that is D NH, and if says no, then sigma present or not we will ask. If yes, then that is D and D, and if no, then that is DN. Okay, so like this we can categorize. And now this one things we have left with more than CNXs. This is no. After that this is yes. After that we have did if CNX is present or not. No, then I have to do this. And if yes, then I ask these questions. No, then yes is here. Okay, now here that this is no. Now I will do one. Now I will do here. If yes, more than CNX is, then I will ask if yes, then I will ask whether S2N and I collinear with CNXs or not. Questions. If yes, then that is sorry, I have left one thing. This is not here. More than 2 CNXs, then if yes, then that will lie to the facial groups OH, PD and IH. Okay, this will lie here. And one more things here we have to do, that whether CNX is present, yes, and whether CN and NCT present or not. And if yes, then here we will ask one more questions, Here we will ask one more questions. What here I will do ask that whether S2N and I collinear with Cn or not. These questions I will ask. If no, then this, and if this is yes, then that is S2N. That is sorry Sn and groups. So these are the tables. So you can say that first, if you take any molecules, let's say if I take about of the water. Now this is linear or not? No. So this will not go here. It will come to here. And now whether more than Cn exists? No, it is H. So only one Cn exists. So if they come to here, whether Cn is present or not? Yes, it's present. Then now ask Cn and Ca2 perpendicular. This? No. Then it will come here. Sigma H is present? No. Then? No. Then this comes. Sigma is present? Yes. Then this is going to be C2B point group or water. Okay. So you have to travel like this. So you have to ask all the questions. And if let's say CO2, so this groups has that linear molecules. So linear molecules, yes, then it will come to here. Sigma H I and this anyone from this is present. Yes, sigma H is present. Then yes, then DNH point groups will go. Okay. Similarly, if I talk about of that BF3 molecules. So BF3 molecules, whether it is linear? No. So that will come here. Whether more than 2 CN is? No. This has on CN axis, then it will come to here. Whether CN is present? Yes, it will go here. And CN perpendicular to NC2? Yes, this is dihedral groups. Here BF3 is dihedral plane is there, so this is present, so that will go to here. Yes. And whether Sn and I collinear with Cn? No, then this will come. Sigma H is present? Yes, then this is going to be DNH point groups, that is D3H point groups. Okay, so like this you have to go. Okay, so this the tables we can draw to look that whether the particular molecules is which point groups it like. So after this we will discuss one thing, that whether change in point group, let's say benzene molecules. If I draw about of the benzene, this is benzene molecules, this is the Habis B6H. So if I go travel this benzene molecules in this here, say benzene, okay, molecule, whether linear or not? No. Okay, it will come to this. Whether more than 2 CNXs, this is actually for cases of that highly symmetric. So this is not so much highly symmetric, so this will no. Then whether CNX is present? Yes. D6 is there, C6 is there, then CN perpendicular NCT? Yes, because that is dihedral groups and dihedral plane is there. Yes, then it will come to here. Whether whether S2N and I collinear with CN? No. Then sigma H is present? Yes, then D6H, because N represents the principal axis. So this will come to D6H. Okay. So now if change in point groups, so if I replace here, all the hydrogens are there. If I replace one hydrogens, so if I substitute one X halogens in place of hydrogen, then what it will look like? This will becomes, here X will comes. So now here the D6H is the point group. So the symmetry elements for D6 is what? C6 is there, obviously E is there, C6, and that is NC2, that is 6C2, that is perpendicular to C6, that is there, and here sigma H is there, and here I is also there, and this C6 and sigma H is there, then S6 is there, and also here 6 sigma B is also there, and what things are there? C6, C2, sigma H, I, S6, S6B. So these are the basic symmetric elements are there in D6H. So now here, since that now the C6 plane was there, C6 the principal axis, here principal axis is C6. Now the C6 will be not possible because this will going, the one atom is replaced, so C6 will be not there. So now we have to pass the plane this, then only we divide it. This is the C2. So here only C2 is there, all here C2 is there, or so C2 is there. So this point group is changed to the C2b. If you replace one halogens, so point elements are E plus C2 plus 2 sigma b. Okay. Now if I replace with two hydrogens, if two halogens, if I substitute, then what will happen? That one H, let's say, I'll draw the picture. So let's say one X is here and one X I placed here. Another, let's say one X is here and another X is here. Let's say another H, one X is here, another X is here. So in this picture, if you look, then its point group G here. Again we can do the C2. C2 is there. Here again you can pass the C2. So here also, here C2 is there, with that sigma H also there, and here sigma H is there. So C2 perpendicular to NC2, then here D2H point group change to D2H. Here the point group is C2b, here the point group is C2b. So if you replace with two halogens, this is changing. Now if I replace with three halogens, then what will happen? Now if I replace with three halogens, then what will the groups looks like? Okay, so here let's say one is here, another comes to be here, another comes to be here. Okay, and one is here, comes to be here, another is comes to be here, another is, let's say one I put here, another I put here, then if one put again here. Okay, so here you see that this molecules is planar. By looking you can say that here D3 is, C3 is here, and also this is a planar molecule, so this is D3H. Okay, so here see the first case, this is D6H was there. After that if we replace one C2b we get, after we replace 2, then this C2b and this is C2b and this is D2H, and whenever I replace with 3, then I get D3H. The point group is sometimes decreasing, sometimes increasing. Symmetry is sometimes decreasing, sometimes increasing. So this is again D3H point groups. And in these molecules, if you look, then I draw also, this is no symmetry elements is there. So this is lies in C1 point groups. Means no symmetry elements is there, or this may be this is planar, then CS is there, and for these molecules, so if you do, then their C2B is there. Okay, so these are the actually, if you changing, substituting, then how the point groups is changing. Okay, so from D2H2 becomes C2B after replacing C2B, and D2H after replace another, then CS, C2B, another is D3H. So this is the changing of point groups after substitution of the atoms or molecules. So after discussing about of that point groups and all these things, we will discuss some characteristics of the uh, characteristics two characteristics of molecules that is understood by point groups. So one is dipole moment, and other is optical active optical active or inactive. Okay, so these two things. So first we will discuss about of uh, dipole moments. So we know that dipole moments, so this dipole moments will have to that atoms to that group. So which groups have first conditions for is that for dipole moment, if Ci, sorry, not Ci, if I, that is center of symmetry, is present, then dipole moments, let's say separate dipole dm. Okay, that's the, I'm giving the shortcut, although this is not correct. Dipole moment, if I is present, dipole moment is 0, first case. And secondly, what is that? If SN axis is present, then dipole moment is 0. Or that is, you can say that sigma H and Cn is present, then dipole moment is 0. Or also you can say that more than one Cn axis. That is, if Cn and Nc2, this is not right to say that. I can say that Cn perpendicular to Nc2 is present, then dipole moments equal to 0. So this things is present, then dipole moment is 0. So from here, what we say that, from here that I can say that Ci, this point groups dipole moment is 0. These point groups dipole moment is 0. From here, what I say that if that S2N dipole moment is there, for that dipole moment is 0. From there, Cn and sigma H, or we can say that this. From here, what I can say that all the dihedral groups, that is Dn, DNH, DND, this dipole moment is 0, or more than Cn axis. So, or more than Cn axis, that highly symmetric groups. So highly symmetry elements, there also dipole moment is 0. Like we say IHTD, OH, here also dipole moment is 0. And sigma H is present, that is like Cn axis, then also dipole moment is 0. So this type of molecules, this type of point groups are present, then dipole moment is always 0. Means dipole moment is active only, so dipole moment is present for the case of CS only, as that is planar symmetry is there, as the C1, another is Cn, another is Cnb. So these type of molecules, these point groups only dipole moment is present, and these molecules here, these two molecules, we can determine directions of dipole moment also. Directions of dipole moment also. Let's say if I say talk about the water, then its dipole moment is here, this dipole moment is here, so equivalent dipole moment is here. And for water also we know that axis C2 axis is dilate. So this is dipole moment is towards Cn axis. Okay, so the directions of dipole moment is towards Cn axis. For this Cn and Cnb molecules, we can determine that dipole moment direction. So we understand that. So if I give the summary, so dipole moment allowed group are Cs, Ci and Cn and Cnb, and dipole moments forbidden group are we can say Ci and or like DNH, DND, S2N, IH, IH, or ITD, PH, and OH, O, all these groups, O, and these all type of groups we have discussed here. Okay, so this is the yes. Okay, so now let's look the second characteristics, that is optical active or not. So for this simple, that is if a molecules H SN axis, if SN axis presents, then this is optical inactive, and if this is absent, then this is optical active. So only one things, that is SN axis, if this is present, then optical inactive, is absent, then optical active. So for SN axis, if presents, then optical inactive, and it is absent, then optical active. This one also we can say that that is symmetric groups, and another is asymmetric, that is disymmetrics, another is asymmetrics. So here first we can say that improper axis, and this is proper axis. So this is present, and here this is absent, so this is present, then optical, and this is present, here it is present, then proper axis present or may not present or absent, there is no problems, that optical active, this is here, so this is optical Here this is inactive because Cn axis is present, then this is inactive. And this, if this is if proper axis is this is d-symmetry, this is present Cn axis, this is Sn, this is Cn, so this is present for case of d-symmetrics, and this is again this is active because this is absent means this is already active, and here this is absent. If this is absent, on that case also this is active, this is also active, but this is here active. Okay, so for checking the optical active, only Sn axis is needed. This is the Sn axis. So if this is present, then this is always inactive, this is improper axis, this is optical. Okay, so if this is present, then this is always inactive, and this is absent, then it is always active. So for disymmetrics, proper axis is present. For asymmetric, this proper axis is absent. That we can say that let's say a molecules. So here Sn axis, here is present, so this is inactive, and let's say here absent, then this is active, and now here that proper axis, this is for Sn axis. Now we say that Cn axis, if present, these are already inactive, now only for naming, this is d-symmetrics and this is asymmetrics. Okay, this a molecules, if Sn expression present, then inactive, if absent, then active. And now if Cn is present, then that is d-symmetric molecules, and this is absent, then that is asymmetric molecules. But the decisions of optical is by using Sn axis only. Okay, this is the just subgroups. D-symmetric is just subgroup of asymmetric is just subset of d-symmetries band groups. Okay, so the summary, if I say that optical active or not, that is Sn axis yes and no. If yes, then that is inactive. If no, then that is active. That's it. Okay, so today after this, thank you.